Welcome everyone. This is tutorial for week 11 of atomic and molecular physics. Uh, Unfortunately, nobody has joined yet. Hoping that some students might join. So I'll wait for a couple of minutes if anybody wants to join. So this is our second last session, and next week will be our last session on same time, Saturday 3 to 5. So yeah, if you want, you can join for the last session. So I'll wait for a couple of minutes before we start, and then we will continue. Okay, so I don't think anyone is going to join. Doesn't matter, you can watch this on YouTube, and I hope you'll find this helpful. So, before doing the problems today, what I would like to do is I would like to mm, write a few key points which will guide us throughout this tutorial on solving the problems. So, this is like a summary of this whole week's content. Okay, so okay, so yeah, let us start. So, the first thing that we'll be doing is so key concepts for uh, today's class. Okay, this is what we will be focusing on today. So, first of all, so number one is vibrational spectroscopy. This is the first thing. So we'll be doing some problems which involve vibrational spectroscopy. So as the name suggests, this involves study of vibrational energy levels of molecules. Mostly we will focus on diatomic molecules as discussed in the class. So these molecules, they can vibrate at some different specific frequencies, And transition between these energy levels is what we observe in spectroscopy. So the spectra that we observe is coming because of transitions in different energy levels of vibration modes. Okay, so basically to important things here. So important things here. One is known as enharmonicity. This is what we also discussed in, like, to some extent in the last session. And this comes because real molecules. So this is like improving our approximation that everything is harmonic. In reality, everything is not ideal. So real molecules don't vibrate perfectly harmonically. So this is so enharmonicity is a deviation from the ideal harmonic model. Okay, so this is the first thing that we should take care of in vibrational spectroscopy. Then second thing that comes is fundamental bands. Overtones. Okay, so as we discussed that there are discrete energy levels and then there are transitions. Okay, so the fundamental band refers to the transition from the ground state to first excited state. Okay, and overtones involve transitions to higher excited states. Okay, like for example, from first excited state to second, or second to third, or first to third, and so on. Okay, so those are known as overtones. So this was vibrational spectroscopy. Similarly, we also have rotational spectroscopy. So just like vibrational spectroscopy studies the vibrational modes and the vibrational energy level transitions, the rotational spectroscopy involves study of rotational energy levels in molecules. Okay, so we know that molecules can rotate, and because they are rotating, they will have certain energy of rotation, and then this energy is also discretized. Therefore, uh, there is possibility of transitions between these energy levels, And when such transitions happen, we can study these transitions using spectroscopy. So we'll get some particular wavelengths. Okay. So then two important things here is moment of inertia. So it is basically, so this is a measure of molecules resistance to changes in its rotation. Okay. So then this is generally denoted by I, and we will see, okay, this is denoted by I, moment of inertia, and this is related to our rotational constant B, which is a property of molecule. So we'll solve some problems where we will find out moment of inertia of molecules. Then, okay, then there is one more thing, which is rotational Raman spectra. So Raman spectroscopy discussed in the class also can also provide information about rotational energy levels. And again, we are not going into details, this is just a summary. So yeah, we'll solve some problems and then we'll have a better idea what we are talking about. Finally, there are a few more things, like there is selection rules. There is selection rules. Okay. So these govern changes in V and J, which are the vibrational quantum number and rotational quantum number, and these help in determining allowed transitions. Okay. Okay. So yeah, basically this is what we will be discussing in today's section and a few more things, and those we can discuss as we move along. So now we can start with some problems. Okay. Let me write down the first problem for today. It will be question 1. Okay, so this is our first problem. We are given a carbon monoxide molecule, CO. It is centered, so the fundamental band is centered at 2143 and first overtone at 4260 centimeter inverse. So from the unit itself, centimeter inverse, we know that they are talking about wave number. So the two wave numbers are given to us. So we have already we already know that if this is our ground state, this is this is first excited state, this is second excited state. So then this transition, this is the fundamental transition. Okay, and this one will give us first overtone. Okay, so from ground state to first excited state is the fundamental, and from ground state to second excited state is our is our first overtone. So here V is 0, here V is 1, and here V is 2. Okay, and then we know the corresponding wave numbers. So let's write down the energy equation. Okay, so this is our equation of energy, that is h nu is hc omega e v plus half, where v is the vibrational quantum number. Okay, so this v is vibrational quantum number. Okay, so we can write the term value or the wave number, which is generally denoted by G. So that is nu by C, and here we can cancel out H, and if we take C to left hand side, we will get this. Okay, so this is the term value, and then we have to find out the difference delta G V, and this is when there is some transition from V prime to V. Okay, then what we get? So then what we get is okay. So now for fundamental 1, we know that V will be 0 and V prime will be 1. Okay, so therefore delta GV will simply become omega E. So V prime is 1, so this will become 3 by 2 minus omega E XE, and then 3 by 2 squared, and then this is 0, so this will be 1 by 2, and omega E XE, 1 by 2 squared. So 3 by 2 minus 1 by 2 is nothing but 1, and this is omega E XE, and this will become 9 by 4 minus 1 by 4, which is just 8 by 4, and 8 by 4 is 2. So let me write 2 here. Okay, and now this is given to us as 2143, correct? So therefore 2143 is omega E minus 2 omega E XE. So this is our first equation. Now for first overtone, V is 0 and V prime is 2. Therefore, the first two terms of delta GV will change. What was our delta GV here? So this will be omega, and V prime is 2, so 2 plus 1 by 2 is 5 by 2 minus omega E XE, 5 by 2 squared, and this will remain the same. Okay, so this becomes 5 by 2 minus 1 by 2, which is just 2, and this is 25 by 4 minus 1 by 4 is 24 by 4, so this is then 6. And this value is also given to us, 4260, right? Let me check. Yes. So 4260 is 2 omega e minus 6 omega e xe. And if we divide by 2, so this becomes 2130 is omega e minus 3 omega e xe. This is our second equation. So if we do 1 minus 2, we get 2143 minus 2130. So WE will cancel out and we will be left with omega e xe. Okay, and this implies omega e xe is nothing but 13. Of course, this is per centimeter, and this is our answer, which matches with option B. Okay, so this was the first problem. We were given a CO molecule, we were given its fundamental band, and we were given its first overtone, and we were asked about the n-harmonicity term, omega e xe. Okay, pretty straightforward problem, little bit lengthy, but yeah, pretty straightforward. So with that, let's move on to the next problem. Okay, so last problem that we did was on vibrational spectroscopy, and this is a rotational Raman spectrum. Okay, Here we have HCl molecule, and we are given the displacements of the exciting lines, and what we are required is to find moment of inertia. Okay, so first of all, let us write delta nu, and the equation that we know is 2b 2j plus 3. Okay, this is what we know, and since delta nu is given to us to be plus minus 62.4 plus 41.6 j, okay, we can write 2b 2j plus 3 to be equals to 62.4 plus 41.6 j. Okay, so let's do a little arithmetic. Let me take out this 2 as common outside, so this becomes j and this becomes 3 by 2. Similarly, let me take out this 41.6 outside, so this becomes j and this becomes 62.4 divided by 41.6. Okay, now note that this thing is nothing but 3 by 2. Okay, this is simply 3 by 2. Therefore, on comparison, okay, upon comparing, what we get is that 4b is nothing but 41.6, and this implies b is equals to, so this will become 110.4, I think, yeah. Yes, correct. So this is the value of b. Now, how is moment of inertia related to b? So, okay, let me write here. So we have two equations. One is that delta mu 2b 2j plus 3. This is one. And another equation is b is h over 8 pi square I c. So these are the two equations which we are using. So using the first, we have calculated b. Now once we know b, we'll plug it in the second equation and we'll get an equation for moment of inertia. So moment of inertia I can be written as h over 8 pi squared b times c. Okay, let's just plug in all the values. Let's also convert b to SI units because the answer is asked in SI units. So this is per centimeter, and if you want to convert it to per meter, you multiply it by 100 and we get this. Okay, so all good now. So this becomes 10 to the minus 42. Let me plug in this in calculator, and what we are getting is okay. So therefore we can write I to be roughly equal to 2.7, so 1 2 3 4 5 into 10 to the minus 47 kg meter squared. So option A. Okay, so this is how we can find out moment of inertia of a molecule if we know the displacement in the Raman spectra. Okay, all good. Let's do next problem. Oh, okay, so this is the third problem, a real lengthy one. Got me some took me some time to write it down. But anyway, let's break it down step by step. Okay, so we are given a diatomic molecule. Let's start with that. Yeah, so we have a diatomic molecule and it has vibrational states with energies EV as h dot omega times V plus half, and then it also has rotational states, okay, with energies Bj plus 1. Here V and J are non-negative integers and these are the vibrational and rotational quantum numbers. This we already know. Okay, so first of all note that the vibrational states are that of ideal harmonic oscillator. There are no enharmonic terms, so we are good there. Then we have to consider, okay, I disconnected, just give me a minute. Sorry for the internet issues. Okay. Yeah. Okay, screen is now visible again. It's a little blurry, but I hope this will improve. Okay, yeah, better now. So then, yeah, so yeah, let's revisit this. So we have a diatomic molecule and we have to consider both vibrational states and rotational states. We are given energies of both of them. We are also given that V and J are non-negative integers. So they start from 0, go 1, 2, 3, so on. Okay. Then we have to consider transitions in both vibration and rotational modes. And this should be restricted by that V is less than equal to 1, so either 0 or 1, and J less than is equals to 2, so either 0, 1 or 2. Then we also have to mind the selection rules, that is delta V is plus minus 1 and delta J is plus minus 1. Finally, what we are asked is the largest allowed energy transitions. Okay, so for vibration, okay, So for vibration we have only two states, and there is only one possible transition. So we cannot do anything about that. There's only one possible transition. But for rotation, we have three possible. These three are there, and therefore by selection rules these two transitions are possible. Okay, these two are possible. Okay, so, and of course, like the reverse also, like 0 to 1 and 1 to 0, 1 to 2 and 2 to 1. These are the possible transitions. And then we have to calculate largest allowed energy transition. This is what the question is asking us. Okay, largest allowed energy transition. So let us start. So first of all, EV, which is for vibration, that is h cut omega v plus half, and EJ, which is for rotation, that is Bj j plus 1. Okay, therefore E total, okay, not therefore, so E total is simply EV plus EJ okay. So for transition between V and V prime, J and J prime, delta E, that thing will become h cut omega, and V prime minus V plus B J prime plus 1 minus B J plus 1. Okay, so this we can rewrite. So this will be delta V. Let's take B common. Right, so this just becomes J prime plus 1 minus J plus 1. So this becomes J prime squared plus J prime minus J squared minus J. So this just becomes J prime plus J prime minus J plus J prime minus J. Okay, So these two, basically j prime squared minus j squared, they give us this. So a squared minus b squared is a plus b minus b. Okay. So once this is done, now we know that delta nu is plus minus 1, delta j is also plus minus 1, and nu less than equal to 1, and j less than equals to 2. So of course here the largest energy we will get is by putting delta v equals to 1. So this term is sorted. So delta v is 1 simply. Then for this term we have j prime plus j, j prime minus j. So j prime minus j again is nothing but this is delta j, and delta j is again 1. So this will be j prime plus j, and this will put as 1, and this will also put as 1. Okay, now to maximize j prime and j, we have to take the two largest values. So we will take 1 and 2. Okay, so j prime is equals to 2 and j is equals to 1. This gives delta E as h cut omega plus p 2 plus 1 plus 1, or h cut omega plus 4b. Okay, so which is option B. Okay, so what we could have also done is we could have taken j prime as 1 and j as 2, but then we would have gotten a negative sign, and that would be h cut omega minus 4b, which is not the largest possible energy, right? That is not the largest. Here both are positive, h cut omega is positive and 4b is positive. Therefore, this is the largest possible energy. Okay, so that was question 3. Let's move on to the next one, which will be question number 4. Oh, internet. Okay, yeah, we are back. So this is question number 4. And you can see it is a pretty simple problem. We are given a diatomic molecule of carbon monoxide. We are also given the transition J is equals to 0 to J is equals to 1. So this is a rotational spectra which we are talking about, and we are asked to find the absorption line occurs at a frequency of. So what frequency is the line of absorption occurring at? We are also given the moment of inertia of carbon monoxide molecule. Okay, so first of all, we know that we can find out the rotational coefficient B. Okay, it is related to I. This is the one, right? We used it in second problem. Yeah, h over 8 pi squared IC. Okay, so we know this. So yeah, first let's calculate B. So B will be 6.626 IA is given to be 1.46 10 to the minus 46, and this is 3 times 10 to the 8. So minus 46 plus 8 is 38. So this then becomes 6.626 into 10 to the 4 divided by 8 pi squared into 1.46 into 3. Let me calculate. So this comes out to be 0.01916 into 10 to the power 4 is 1, 2, 3, 4. So then B is nothing but 191.6 per meter. Okay, so this is what we have. Now another thing that we know is, we know that energy of rotation, it is given by this equation bjj plus 1. Okay, let's also write it down. E is bjj plus 1. Okay, so delta E will be B times J prime plus 1 minus J plus 1, and here the transition is given from 0 to 1. Okay, so when this is 0, so this term becomes 0, and when this is 1, so this is 1, and 1 plus 1 is 2, so this just becomes 2b, right? And this is nothing but h nu, so nu then becomes 2b by h. Okay, so nu will be 2 into 191.6 divided by 6.626 into 10 to the minus 34. Oh no, not like this, but our nu will be h by I j plus 1. So this will become 1.0546 into 10 to the power minus 34 plus 46 divided by 2 pi into 1.46, or this will become 0.11496 into 10 to the power 12, or roughly 1.15 into 10 to the power 11. So our frequency is 1.15 into 10 to the power 11 Hertz. Okay, so I missed out on one formula which I'll write here. So the formula is this is the formula for moment of inertia. This we also used in the last session, and this gives us the answer in a pretty straightforward way. Okay, I complicated the problem, my bad. But yeah, if you want further clarification, please ask me in the forums. Okay, let's move on to the fifth one. Just wait a minute. Okay, small water break. we are back. Okay, somebody joined actually. So, hi Satish, we are currently doing okay. Never mind, Satish left, so no need to explain. Yeah, this is the fifth problem for today. The first absorption spectra of C12O16 and C13O16 are respectively at 3.842 and 3.673 per centimeter. So we have two isotopes of carbon and their absorption spectra are obviously at different locations because they have different masses, therefore they will have different moment of inertia and therefore different B and everything different related to rotation. Okay, so what we are asked is to calculate the ratio of magnetic moments of C13O16 to that of C12O16. Okay. Okay, so as we said that the rotational term, this is the rotational term, right, denoted by F. So this is Bj, J plus 1. This is the rotational term, and here B is related to moment of inertia, and this B is rotational constant. So B is inversely proportional to moment of inertia. Let me write it here. So B is inversely proportional to moment of inertia. Also delta Fj this is Fj plus 1 minus Fj. Okay, so this becomes B j plus 1 j plus 2 minus b j plus 1. Okay. So this just becomes okay, we can take bj j plus 1 as common, and then we'll get j plus 2 minus j. So this j will cancel out, and this will be 2b j plus 1. Now for first absorption, j is 0, so this implies delta f0 is simply 2b. Okay, therefore delta f0 for C12O16 divided by delta f0 for C13O16. This will be nothing but 2b of C12O16 and 2b of C13O16, and because they are inversely proportional to moment of inertia, so this will be moment of inertia of C13O16 divided by C12O16. Okay, now these rotational terms are given to us, so they are 3.842 and 3.673. So we will get 3.842, 3.673. This thing will becomes, let me write this as 13 and 12 for C13 and C12 respectively. Okay, this implies I13 divided by I12, this comes out to be 1.046. Okay, which is option B. And okay, I think there's a typo here. This should not be magnetic moments, but moments of inertia. Okay. So having done this, let's do one more. Okay, so the question asks us which of the following molecules produces vibrational spectra but not rotational spectra. So it should give us vibration but no rotational spectra. So I think this was discussed in the class that this is related to permanent dipole moment. Okay. So what is the concept? The concept is if a molecule has permanent dipole moment, then it produces rotational as well as vibrational spectrum. So HCl, of course, this is plus, this is minus, so it has a dipole. Now CCl4, you have Cl, Cl, Cl here. Now you can note that the charge distribution is symmetric about carbon. So this does not have no permanent dipole. This does not have a permanent dipole moment P. And CO again plus minus, you can see it has a dipole. Similarly NaCl plus minus also has a permanent dipole. Therefore option B, which is the odd one out, because it doesn't have a permanent dipole moment, it can produce vibrational spectra but not rotational spectra. Okay. So question 7. Okay. So let me have a water break. Yeah, so we are back. So this problem is about hydrogen fluoride molecule, which is HF. Okay, and it has absorption line in the rotational bond at 40 centimeter inverse. So this is the absorption line in the rotational band for 18F. And now we want to find the corresponding line of HF for isotope 19F. Like by how much will it be shifted? Okay, so in the last problem, we got this one equation that this delta F0 is simply equals to 2b. Okay, that is simply equals to 2b. So here we can write 2b1 is 40 centimeters. Okay, or b1 is simply 20 centimeter inverse. Okay. Also, we know that b is equals to h over 8 pi squared times I c. If we write the moment of inertia in terms of reduced mass, so we can write as mu r squared. Okay. Therefore, h over 8 pi mu 8 pi squared mu r squared times c is 20. This is mu1. Okay. For 18F molecule. Okay. Similarly, we will get another equation mu2 r squared c, and let's call this as b2. Okay, so this implies that if we divide b2 by 20, if we divide both these equations, everything will cancel out and this will be just mu1 by mu2. So b2 is nothing but 20 times, and mu1 is, because h is 1, into 18 upon 1 plus 18 divided by 1 into 19 upon 1 plus 19. Okay, so b2 becomes 20 times 18 over 19 multiplied by 19 multiplied by 20 over 19. Yeah. So this becomes 19.94 per centimeter. And therefore, if we want to find out the shift, so 2b2 will become this much, and it was 40 per centimeter. Therefore, the shift is given by 2b1 minus 2b2, which is 40 minus 39.88, and this is 0.12 per centimeter. Okay. Therefore, the spectra will be shifted by 0.12 per centimeter, and this is our final answer, which is option A. Okay, so this was the 7th problem. Let us now do question number 8. Let me write down question number 8. Okay, so this is one more problem based on vibrational spectra. We are given transition from V is equals to 1 to V is equals to 2. Okay, let us again draw some energy level. V is equal to 0, V is equals to 1, V is equals to 2. Okay, and this is the transition. V is equals to 1 to V is equals to 2. And both are, all are equally spaced, all have the energy separation h cut omega. Right? Why? Because there is no n-harmonicity. We are required that we do not consider any n-harmonicity in the problem. Okay, and what we are asked is wave number 1 by lambda. Wave number 1 by lambda in terms of vibrational constant omega. Okay, so let's begin. We know that E is equals to h nu v plus half. This is hc by lambda. Okay, h cancels out, so 1 over lambda. This becomes nu over c v plus half, and here you can see that nu over c is omega. So this is omega times v plus half. Okay, now for transition, from 1 to 2, we get 1 by lambda v is equals to 2 minus 1 by lambda v is equals to 1. This will be omega times 2 plus half minus omega times 1 plus half. Okay, so this is how much? 5 by 2 omega, and this is 3 by 2 omega. So 2.5 minus 1.5 is simply omega. Okay, therefore required wave number is omega. Which is option B. Okay, so let me write down the next problem. So we'll solve 2 more and then we'll call it a day. Okay, so question number 9, I guess. All right. So a very simple problem. If you have done the problems based on last week, so you would be able to do it easily. We did a bunch of problems in the last session which were very similar to this. So we are given a carbon monoxide molecule and we are required to find the vibrational energy for V is equals to 2. Now we are given several things. We are given the force constant, we are given reduced mass, and we are also given value of Planck constant, which we more or less know. Okay. So let me connect my laptop to power. So yeah, let's do it. Okay. So this is what we discussed in the last week's tutorial, that when we consider a harmonic oscillator model for a molecule, then we can write the frequency of oscillation mu as 1 over 2 pi and under root k over mu. Okay, now all these things are given to us, so let's plug in the value of k and mu. So k is given to us as 1870 Newton per meter and mu is given to be 1.14 10 to the minus 26 kg. Okay, so this becomes 1 over 2 pi under root 1870 1.14 10 to the minus 26. Okay, so this becomes 1 over 2 pi under root 1870 divided by 1.14, and this 10 to the 13 will come up. Yeah, so this much hertz. So then this new becomes 1870 divided by 1.14. So this comes out to be 10 to the 13 into this comes out to be 40.5 roughly, and then divide by 2 pi. So let's do that. Divide this by 2. So this becomes roughly 6.45 10 to the 13 hertz. So we have calculated the fundamental frequency of oscillation nu. Okay, so this is our fundamental frequency. Okay, now for any value of rotation, sorry, this is vibrational quantum number V, the energy is given by E is equals to h nu and V plus half. Okay, so let's plug in the value 6.626 10 to the minus 34, and this is 6.45 10 to the 13, and this is V plus half. Okay, so yeah, this much joules. So if we multiply we get these things becomes 4.27 into 10 to the minus 20. Times V plus half. Okay. Now we are asked about V is equals to 2. So for V is equals to 2, E2 will become 4.27 into 10 to the minus 20, and multiply this by 2 plus half, which is 2.5. Yeah. So into 2.5, and this becomes 10.68 into 10 to the minus 20 joules, or 106.8 into 10 to the minus 21 joules. So E2 is roughly this value, 106.8. Okay, we can write 4 here just to match with the answer exactly. So it matches with option A. Okay, so A is the correct answer. Okay, so last question for the day, and then we are done. This will be question number 10. Okay, very similar to the last problem. Here we have H2 molecule. Okay, again this behaves like a harmonic oscillator. We are given the force constant and we are also given the reduced mass. What we are asked to find is the vibrational quantum number V. Okay, we are asked V. In the last problem we were given V and we were required to calculate the energy. Here we are given the energy, right? We are given the energy corresponds to V. So let's write down what we are given. So first of all, we are given that K is 575, mu is 8.35, okay. Let me write down properly. This is mu. Then we are also given that energy corresponding to the vibrational quantum number V, that is given to be 3.936 10 to the minus 19 joule. Okay, so we will begin how we began in the last one. First of all, we will calculate frequency of oscillation. Frequency of oscillation is given by okay, so we'll plug in the values. This will be square root and this 10 to the 14 will come out. Okay, this much hertz. So if we plug in the calculator, okay, so we get nu is equals to 1.32 into 10 to the power 14 hertz. So this is nu. Okay. Now energy of harmonic oscillator is given by E for any quantum number V. This is nothing but h nu and V plus half. And this is given to us to be 3.936 into 10 to the minus 19. This is 6.626 into 10 to the minus 34. And this is 1.32 into 10 to the 14 multiplied by V plus half. This implies V plus half is equals to 3.936 divided by 6.626 multiplied by 1.32, and let me take out, so this is minus 34 minus 14, so this is minus 20, and here it will become plus 20, so just multiply by a 10 here. Okay, so let me pull out my calculator again. So yeah, this comes out to be 4.5, and we can write v as 4.5 minus half. So this gives us v as 4. Okay. The required vibrational quantum number is 4, which is option B. Okay, so okay, yeah. So this was the last problem, and here, similar to the previous problem, we are given the force constant, effective mass, and using that we can get the energy, or we can get the vibrational quantum number if the other one is given. Okay, so yeah, that's all for today. Thanks for watching. If you have any queries, please post them in the forums or in the YouTube comments, and I'll try my best to reply as soon as possible. So yeah, I'll end this session, and next session will be the last session, which will be next Saturday, same time, 3 to 5. Yeah, please feel free to join, ask your queries. I don't think I'll be taking the additional session, so that will be the last session before your exams. Okay, so try to join, and if you want to discuss anything based on next week's lecture and earlier lectures, you can discuss anything. Okay, so okay, thanks for watching. See you next week. Bye bye.